There is a mountain in Sicily that is falling apart in slow motion. And what makes this different from every other geological hazard we've discussed is that we can see it happening. We can measure it. We have the instruments to track its descent. And yet we remain largely unprepared for what comes next. I'm talking about Mount Etna, Europe's most dangerous volcano. And right now, every single hour, its southeastern flank slides another millimeter closer to the Mediterranean Sea. Most people who live near Etna worry about eruptions, about lava flows, about ashfall that closes airports and threatens neighborhoods. What they should be worrying about is the mountain itself disappearing into the ocean. Let me explain what's happening beneath Sicily, because this involves some of the most fundamental physics of how mountains fail. Mount Etna rises 3,350 meters above sea level. That's what we see. The iconic peak visible for hundreds of kilometers. But the mountain's foundation extends another 1,000 meters below the waves, invisible from land, unsupported by solid ground beneath it. This underwater portion is the key to everything. The entire southeastern flank of Etna, both above and below sea level, moves as one coherent block. Imagine a piece of the mountain larger than downtown Manhattan, and picture this massive block sliding slowly toward the abyss. That's what's happening right now, every day, every year. The movement isn't random. It's driven by gravity acting on steep underwater slopes. Etna sits on a complex geological foundation where the African tectonic plate dives beneath the Eurasian plate. This collision creates layers of clay-rich sediments. Think of clay as a lubricant, a natural layer that allows millions upon millions of tons of volcanic rock to glide across weak geological plains. The mountain is literally undermining itself, 1 centimeter at a time. The measurements are precise and relentless. GPS stations scattered across Etna's flanks record the same truth. The southeastern slope moves seaward at 3 to 5 centimeters every year. Not erosion, not settling, gravitational collapse in slow motion. At that rate, the mountain's foundation shifts about 1.5 meters per decade over a human lifetime. That's measurable displacement. Over geological time, it's a death sentence for the mountain's stability. Dr. Geppi Puglisi from Italy's National Institute of Geophysics and Volcanology has spent his career tracking this movement. His weekly bulletins, updated as recently as November 2025, show something unprecedented. A mountain that erupts violently while simultaneously falling apart. The volcanic activity masks something far more dangerous underneath. When Etna erupts, it doesn't just release pressure from the magma chamber. It adds weight. Fresh lava pours down the slopes. Pyroclastic flows race down volcanic channels. All of this material is loading the mountain, adding burden to a slope that's already sliding. In August 2025, something changed. New fissures tore open across the southeastern flank. Lava cascaded 2 kilometers down slopes that were already moving. Strombolian explosions, the kind that shoot blocks of molten rock into the air, lit the Sicilian night sky. But this wasn't just another eruption. This was loading. Every ton of fresh lava was adding weight to a mountainside already primed for failure. Multiple fissures distributed volcanic material across already unstable terrain. What used to happen over decades now happens in weeks. The mountain is piling weight onto its own foundation while that foundation slides toward the sea. Now here's where it gets truly remarkable. In 2016, scientists did something never attempted before. They placed acoustic transponders on the seafloor off Etna's coast. These are sophisticated instruments typically used to study deep ocean fault systems, deployed in water over 1,000 meters deep. What they recorded changed everything. In May 2017, the instruments detected something extraordinary. The underwater portion of Etna's flank moved over 4 centimeters in just 8 days. Not during an eruption, not during an earthquake. The mountain's foundation was simply sliding away, pulled by gravity into the abyss. The movement was aseismic, meaning it happened without the violent shaking that typically accompanies major geological events. But here's what troubles me most. This isn't unique to Etna. It's not an isolated phenomenon. The pattern has happened before. 8,000 years ago, Etna did something that still haunts the Mediterranean seafloor. Marine sediment cores pulled from the Ionian Sea, samples drilled from deep ocean bottom, reveal massive debris layers, volcanic ash mixed with rock fragments, the geological fingerprint of catastrophic collapse. These cores, extracted by research vessels, tell a story written in mud and stone. The ancient event left its mark across the entire Mediterranean basin. Elevated marine terraces along distant coastlines bear witness to waves far larger than any recorded storm. Coral formations on Greek islands show damage patterns consistent with massive tsunamis. Archaeological sites around the Mediterranean show sudden abandonment layers that align with the timeline of Etna's ancient collapse. Computer reconstructions estimate that the collapsing volume exceeded 10 cubic kilometers, enough material to bury entire cities. The resulting tsunami radiated outward at speeds approaching 800 kilometers per hour. It reached North African coasts within 3 hours. It maintained destructive power across thousands of kilometers, and we don't have to look that far back for warnings. In 1888, Ritter Island volcano in Papua New Guinea suffered a flank collapse, generated a tsunami up to 60 feet high, killed hundreds along distant coastlines. The collapse happened without warning. One moment the mountain was there. The next moment it was in the sea. Eyewitness accounts describe the ocean retreating, then returning as a wall of water that swept away entire villages. More recently, in 2018, Kilauea's southeastern flank collapsed into the Pacific during an eruption, created new underwater canyons, reshaped Hawaii's Big Island forever. The seismic monitoring detected progressive failure as rock weakened by magma intrusion finally gave way. The parallels to Etna are unmistakable. Submarine monitoring off Hawaii revealed aseismic sliding, the same slow movement we see at Etna before the catastrophic collapse. The geological structure mirrors Etna's foundation, a volcanic edifice built on weak sedimentary layers. Even the rate of pre-collapse movement matches current measurements from Sicily. This tells me something profound. Each collapse follows predictable physics, but unpredictable timing. Millions of cubic meters of rock and debris avalanche into the sea in minutes. The water displacement is catastrophic. The resulting tsunami energy approaches that of major earthquakes. But instead of shaking land, the energy is focused entirely on moving water. Now imagine that physics applied to the Mediterranean. Catania, Sicily's second largest city, has 300,000 people living directly on Etna's unstable flank. They've adapted to ash that closes airports. They've prepared for lava that threatens neighborhoods. They have not prepared for the mountain itself to fall into the sea. A major collapse could displace between 1 and 10 cubic kilometers of material into the Mediterranean. Computer models predict initial wave heights of 10 to 50 meters near Sicily. Destructive tsunamis that could reach Greece, Malta, and the North African coast within hours. The wave energy would refract around Sicily's southern tip, focusing destructive power on the narrow Strait of Messina. Reflected waves would maintain destructive power for hours. Multiple tsunami arrivals at each coastal location. The mathematics are sobering. Even a partial collapse could generate more destructive energy to the 2004 Indian Ocean tsunami that killed over 230,000 people. But the Mediterranean's enclosed geography and higher population density along coastlines multiplies the potential for catastrophe exponentially. What's extraordinary is that existing tsunami warning systems designed for seismic events might not detect the unique signature of volcanic collapse until waves were already propagating. By then, for nearby coasts, it's too late. Minutes of warning, that's all a coastal city would have. Minutes to realize the wave is coming. Minutes to decide whether to evacuate or climb to higher ground. The Italian government has issued no evacuation orders, no tsunami warnings. Official statements emphasize gradual processes. Long-term monitoring, ongoing research, weekly bulletins from Italy's National Institute of Geophysics focus on volcanic hazards. Ash dispersal, lava flow modeling, gas emission trends. But behind closed doors, emergency planners are modeling scenarios they hope never to implement. International collaboration has intensified monitoring efforts. Japanese experts, veterans in studying submarine landslides around volcanic islands, have shared acoustic transponder technology. Hawaiian researchers contribute insights from Kilauea's recent collapse. British marine geologists provide seafloor mapping expertise. The Mediterranean has become a laboratory for understanding volcanic flank failure. Advanced monitoring networks now track every measurable parameter: ground deformation, gas emissions, thermal changes, seismic activity, electromagnetic variations. Artificial intelligence algorithms analyze patterns in real time, searching for subtle signatures that might herald accelerating instability. Yet, the debate within the scientific community continues. Some researchers suggest the possibility of acceleration. They align geodetic data with historical patterns that preceded ancient collapses. The same signals appear in current data: subtle changes in sliding rates, shifts in earthquake patterns. These could be precursors. But other experts point to the mountain's remarkable stability. Etna has survived major regional earthquakes, including the devastating 1,693 event that destroyed much of southeastern Sicily. It has endured massive eruptions that added enormous weight to its flanks. Each time, the mountain has adjusted, flexed, continued its slow slide without catastrophic failure. Dr. Murelia Erlab, who led the groundbreaking seafloor monitoring program, describes the situation as a loaded spring. Decades of slow movement have built enormous stress into the mountain's foundation. The acoustic transponder data reveals a system balanced on the edge of stability, where small changes in loading or lubrication could trigger massive failure. But predicting the trigger remains beyond current science. Whether it's a magnitude 6 earthquake, a massive eruption, or simply the accumulated weight of time, we don't know. We can't predict it. What's certain is that Etna defies easy prediction. The same volcanic forces that built the mountain are now tearing it apart. Each eruption adds weight. Internal pressures seek release through the path of least resistance. Gravity's pull toward the sea. The mountain exists in dynamic equilibrium, balanced between construction and destruction, creation and collapse. The physics are well understood. The timing remains a mystery. The mountain keeps its secrets, sliding toward an unknown threshold that may not reveal itself until seconds before it's crossed. And here's what I find most troubling as a physicist. We have the instruments to measure what's happening. We have the data. We understand the physics. But we don't have certainty about when the transition will occur from slow sliding to catastrophic failure. Emergency planners prepare for scenarios ranging from decades of continued slow sliding to sudden catastrophic failure within years. The Mediterranean sleeps fitfully, watched over by instruments that record every tremor, every shift, every sign that Europe's most dangerous volcano is preparing for its most dangerous act. The slow motion disaster continues. Measured in centimeters per year, but capable of unleashing devastation in minutes. This is the paradox of Etna. We can see it failing. We just can't predict exactly when it will finally give way. And when it does, the consequences will reshape the Mediterranean basin forever.